In this video, we are going to work on this problem. It says find the intervals on which f is increasing and then also decreasing. All right, and we have this function f here. F of x equals x to the 11th over 11 minus x to the 7th over 7 plus 2. Okay, so the first thing that you want to do is just find the domain of f. And this function is a polynomial, and so therefore the domain of any polynomial is negative infinity to positive infinity. Okay. Next up, we want to take the derivative of this function. It's a little easier if you just rewrite the x to the 11th as the x to the 11th over 11 as 1/11th times x to the 11th, right? These things are equivalent because if you put this x to the 11th over 1 and then multiply the two fractions, you'll get exactly this. So this and this are the same. The benefit of doing it this way is that we can use the constant multiple rule to take the derivative instead of the quotient rule. All right, so I'm going to do the same thing here. I'm going to write x to the 7th over 7 as 1/7 times x to the 7th, and then plus 2 on that. Okay, so now we're ready to take the derivative. Okay, so this function, this polynomial, is the difference and sum of functions, right? So using the sum and difference rules, all we need to do is to take the derivative of each individual piece and then subtract and add them together. All right, so starting on this first term right here, we use the constant multiple rule. We have a constant, a number times a function. So the constant multiple rule says just rewrite the constant and then multiply by the derivative of the function part, and that is a power function. So we would use the power rule, which says bring the power down and drop this by 1. All right, and then the difference rule says then subtract off the derivative of this piece. So again, we would use the constant multiple rule. We get 1/7. Just rewrite the constant and then multiply by the derivative of the function. And that again is a power function. And so using the power rule, we bring the 7 down and subtract 1. Then the derivative of this plus 2, right? The derivative of 2 just by itself, since it's a constant, the derivative would just be 0. And so I'm not going to bother to write the plus 0. All right, the next step in the process is then to simplify the derivative as much as possible. There's not a whole lot to do here. We just multiply these numbers out. So 1/11th times 11 is just 1, which again, I'm not going to bother to write. And then 1/7 times 7 is just 1 again. So we wind up with x to the 10th minus x to the 6th. Okay, so next up is to figure out which intervals f is increasing on and on which intervals it's decreasing. Then what we want to do is to solve the inequality f prime of x greater than 0. All right, so that inequality is going to be x to the 10th minus x to the 6th greater than 0. That is a polynomial inequality. In order to solve that, what I am going to do is to set it equal to 0 and solve that out. So I would try and factor this polynomial as much as possible. The first step in factoring a polynomial is to factor out the greatest common factor. The greatest common factor here is going to be x to the 6th. So when I factor that out, I'm going to get x to the 4th minus 1. All right, and then this is the difference of two squares. So it can be factored. like so. And then this x squared minus 1 is also, again, the difference of two squares. So it can be factored as well. Let's see if I can write this down here. It factors to x minus 1 times x plus 1. Okay, so, and then this is the sum of two squares, which does not factor unless you use complex numbers. So just leave it the way it is. Okay, so we have everything completely factored here, and when we multiply all these factors together and we get 0, we know that at least one of these factors had to be equal to 0. So we're going to go through and set each one of those equal to 0, and then solve those out. So let me move up here to the top. So I'm going to take and set x to the 6th equals 0. I'm going to take x minus 1 and set it equal to 0. I'm going to take x plus 1, set it equal to 0. And I am going to take that x squared plus 1 and set it equal to 0. And I'm going to solve each one of those. Okay, so first one is x to the 6th equals 0. The only solution to that is 0 itself, right? If I take any number and I raise it to the 6th power, right, and I get 0, well, the only way that that could be is if the number were 0 itself, right? So if x to the 6th is 0, then x has to be 0, right? Because if the number was positive, well, a positive number to the 6th power is a positive number, not 0. So this can't have any positive solutions. And if it were a negative number, right, to the 6th power, then the result would also be positive. And so therefore it couldn't be 0. 0 to the 6th power is 0. So the only solution off of this is x equals 0. Here I get x equals 1. Here I get x equals minus 1. And on this one, this is a quadratic. It's one of the easier types of quadratics because the x term, right, is missing. So you can solve for x squared and then use the square root property. So when I do that, I get x squared equals minus 1. Right? And so I have solved for the x squared. So then take the square roots of both sides. You're going to have x equals plus or minus, right, the square root of negative 1. I have a negative underneath the square root, right? So that comes out as the complex number I. And the square root of 1 is just 1. And 1 times anything is just itself. So I wind up with two solutions here, plus I and minus I. Okay. Well, those are complex numbers, right? And so in this problem, that's not going to factor in, okay, to this. So we would just throw those out. There is calculus with complex numbers, and in that case, we would keep those, right? But this is only a real number calculus, right? So those just get thrown out, right? Okay, and so what we wind up here with are three solutions, 0, 1, and minus 1. So those are our possible critical numbers. So we need to write those down. Okay. Next up, what we need to do is to put these possible critical numbers, all the possible critical numbers, on a number line that represents the domain of f prime. Okay, so make sure you put them in the right order, right? Respect the order of the number line. And so that's what we would get. All right, and so then what we need to do is to pick some test points on each of these intervals, right? These possible critical numbers divide the domain of f prime into 1, 2, 3, 4 pieces, right? So we need to pick a piece on each of those. So I'm going to pick 2 over here. I'm going to pick a half in here. I'm going to pick minus a half in here. And I'm going to pick minus 2 on this piece, right? And then I'm going to take those test numbers and I'm going to plug them into this inequality right here, x to the 10th minus x to the 6th, okay? And then see what I get when I do that, all right? The numbers, right, I don't have a calculator here. If you have a calculator, it's pretty easy just to plug these numbers in and see whether you get a positive or negative, right? I don't have a calculator, or I don't want to switch back and forth between one. So what I'm going to do is use this version, right, of the derivative, the factored out version, okay, instead of doing that. So I'm going to be plugging my, I'm going to take this inequality and replace this with this expression right here, just because it's easier to do by hand. Now, when you do that, you have to be really careful that you use, right, that whatever you're using is exactly the same as this expression. So you do have to be a little bit careful doing that. All right, so I'm going to look at this x to the 6th times x minus 1 times x plus 1 times x squared plus 1 greater than 0. That's where I'm going to be plugging my test numbers into. Okay. All right, so first I'm going to start with 2. So I get 2 to the 6th times 2 to the minus 1, or 2 minus 1, times 2 plus 1 times 2 squared plus 1 greater than 0. Okay. All right. So when I do that, I get 2 to the 6th. Well, 2 to the 3rd is 8, right? So I'd have 2 to the 3rds. So that is going to be a 64. That's going to be a 1. That's going to be a 3. And this is going to be 2 squared is 4. 4 plus 1 is 5. Okay. So I get 64 times 15. Okay. And that's going to be 640 plus 320, right? 640 plus 320 is 960, I think is right. Okay. All right. So I get 960 right on that one. So that means that 2 is a solution to this inequality right here, right? All right. And so again, it's on these pieces, it's all or nothing. Either every number to the right of 1 is a solution, or none of them are a solution. Okay. So so that means that all of the numbers on this part of the number line are solutions, okay? And so therefore, when I plug them in, any of these numbers into the derivative, I am going to get a positive number, okay? So what I do, right, is put a little plus sign where that 2 is. So just go in here, and I put a plus in here to let me know. Also, one part I forgot to do here on the number line was to identify which of these possible critical numbers are critical numbers. Remember, they have to be in the domain of f, and so therefore, since the domain of f is all real numbers, all of these are critical numbers. So this is a critical number, this is a critical number, and this is a critical number. Okay, so if you notice here, what I really care about is whether I get a plus here or a minus here in the derivative, okay? So I can shorten this process up a little bit when I go to do the next test point, because if I look, it doesn't really matter what number I plug in to x to the 6th power, because this is an even power. I'm always going to come up with a positive right here. So when I go to plug in the number in the next test number, I'm really not going to plug it in into this. I'm just going to keep in mind that whatever I get when I plug this in here, it will be a positive number. The same thing is true for this factor over here. If I have x squared plus 1, well, it doesn't matter what real number I plug in there, I'll get a number that's 0 or bigger. And then when I add a 1 to it, right, I will get a positive number. The result of plugging any real number in for x into this factor will be a positive number. So again, I can shorten my work a little bit, right, because I really only care if this is positive or negative for this problem, right, because we're doing increasing, decreasing. So I can shorten up my work on the next test point by just realizing that, hey, if whatever number I plug in, this is going to give me a positive number right here. Okay. All right, so let me erase a little bit of this so we can plug in the next test number. All right, so the next test number is a half, right? So I'm going to plug a half in here. I would get half minus 1, and then a half plus 1. All right, and so you can see when I do that, a half minus 1 is going to be minus a half. A half plus 1 is going to be 3 halves. All right, and so what I have is 1, 2, 3 positive numbers and 1 negative number. When I multiply all that together, I don't. The number that I will get will be a negative number, right? Because positive times a positive times a positive is going to be positive, and then a positive times this last negative will switch it to negative. So you can see just looking at the signs makes your work a little bit easier in here. If you don't like this trick that I'm showing you, then you can just use a calculator to crank this right out and see whether it's positive or negative. Okay, so don't get too confused by it if you find that confusing. I'm just doing it to shorten up the work a little bit up here. All right, so I plugged in a half. I'm going to go back up here, right, and put a minus there on that piece. All right, next up, I need to plug in this negative 1/2. When I plug in this negative 1/2 on here, here I have negative 1/2 minus 1. That's going to come out to be a minus. And when I do negative 1/2 plus 1, that's positive 1/2, right? And so here I have a positive times a positive times a positive. And then times this negative, I am going to get another negative right in here. Okay. So when I plugged in the test number negative 1/2, I get a negative. So going back up here, I would put a big minus sign right over this. All right, and then the last number is a negative 2. So I'm going to plug that in and see what I get. All right, negative 2 minus 1 is a negative 3, and negative 2 plus 1 is a negative 1. Okay, so looking at that, I would have these two negatives, right, would multiply together to make a positive, and then multiply by two other positive numbers that means the number that I get when I plug the negative 2 in to the derivative will be a positive number, right? So that means that every number, right, on this piece up here, when I plug it into the derivative, we'll get a positive number, like that. All right. So there is my sign diagram that I need for this problem. Okay. And so now, once I have that sign diagram, then it's pretty easy to figure out where it's increasing or decreasing, because all I really have to do is to look at the sign diagram. All right, so I'm going to erase this work in here. And then we will write the answer for increasing and decreasing. Okay, so we want to know where the original function is increasing. So those are going to be the intervals where there is a plus. So here's the first one, right? So that's going to be negative infinity to negative 1. All right, in my class, I'm just always going to leave these as parentheses. But if you're in somebody else's class, your teacher may want you to put a bracket on here, right? That's going to be, depends on how your teacher defines increasing. It's not super consistent among calculus textbooks and teachers. So just to avoid, more confusion about whether this should be a bracket or parenthesis, in my class I just say, hey, just leave these as parentheses for right now. These problems are, have a lot of steps to them anyway, so just not going to add extra steps on there. But if you're taking somebody else's class, then you need to be a little bit, you might need to be more careful about how you do this. And it's also going to, if you're working from a book by yourself or something like that, in the book they might have brackets here. Okay, it depends. I've seen it both ways. All right, and you could argue about what's better, for learning and as opposed to the technicalities of it. All right, so over here is another interval. It's a plus on this interval, so that would be from 1 to infinity on that piece. Okay. All right, and then decreasing. All right, so this interval here between negative 1 and 0. And this interval over here from 0 to 1. All right, and so again, you might ask, hey, can I write that as the interval from negative 1 to 1? And again, it kind of depends on how you define the increasing. If you define it where as this being where the derivative is less than 0, then no, you can't. But in other books, the usual definition of increasing, you can do that as long as this is in the domain of the original function. But in my class, again, on the quizzes that you take, just pick. It's going to be written like this, okay? So don't worry too much about that. But again, if you're in somebody else's class, then you might need to combine those. Your teacher might might tell you specifically, hey, you need to make this as big as possible. So okay, and so that's it on this one.